بسم الله الرحمن الرحيم. اللهم صل على محمد وعلى محمد. My name is Yusuf Al-Jawad, G 2024-02640. We're going to examine the characteristics of reflected and standing waves and observe the behavior of signals under different load conditions. We're going to be setting up an experiment using this program with the following design setup. We have this program. We're going to set the impedance of our line to 50 ohms, which is equal to the impedance of our line. We're going to generate a signal with a time-dependent voltage source and examine the effect of the load on the signal. And we're going to do the same on the right-hand side, where the line impedance is equal to the load impedance. As you can see on the left-hand side, the load impedance is equal to the line impedance. The result is a lack of any reflected signal, which means that there's no interference between the incident wave and the reflected wave. The signal travels smoothly, forming a continuous sinusoidal wave that's unaffected by reflections. Let's take a look at the trace. It's very neat and organized. And take a look at the envelope. It neither attenuates nor amplifies. It stays roughly the same all throughout, exactly the same all throughout. However, when the load impedance differs from the line impedance, a portion of the signal reflects back. When we examine the trace like this, we see fluctuations in the signal, which is these dips right here. This is due to the interaction between the incident and reflected waves. This is just due to simple superposition effect, because the reflected wave is weaker than the incident wave. Their combined amplitude does not cancel out completely, resulting in oscillations. Let's take a look at this graphic. Here we have a generated signal called the incident wave. And it travels from the generator to the load. If the load impedance matches the line impedance, there will be no reflected wave. The reflected wave, which is this blue line right here, will be 0, indicating no reflection. It'll be a flat line. In this scenario with no reflection, the red wave remains undisturbed, maintaining a constant straight line, essentially without any reflected wave. The signal behaves as though there is no interference, appearing as a steady signal. However, if the load impedance doesn't exactly match the line impedance, a portion of the signal will be reflected back. In this case, the reflected wave, the blue one, is not equal in magnitude to the incident wave, but instead it's attenuated or becomes weaker. As a result, the combined waves, which is this black signal right here, may come close to the 0 axis, but doesn't completely, which we can see right here in the envelope. It dips down, but it never completely reaches 0. If we come back here and stop the animation, and let's take a look at our phasor plots. Standing wave pattern, and do the same on the right-hand side over here. On the left-hand side, where the line impedance is equal to the load impedance, you have no change in your voltage or your current throughout the signal. This is because there's no reflected signal and it's just zero. Whereas in this side over here, if uh, on the side over here, it's essentially a static phasor. We can see a steady phase shift throughout the signal due to the difference in the line impedances, which is these peaks right here and here. What can also be assessed from the phasor plots in the right-hand side is that this is a summation of both the incident and reflected wave. And due to the superposition of the waves, you receive a smaller signal. Like this is not the same peak as the incident wave, and it's not larger, it's smaller. So what we're going to do now is go back to the beginning, and we're going to be adjusting our impedances. So here we set our line impedance to 0, and on the right-hand side, we are going to set our load impedance to a very large value, near infinity, or as close as you can get. Update the values, and once again, time-dependent voltage against time, and let's see what the signal shows. And let's do the same on this hand, on the right-hand side. So when we view the signals in the time domain, the left-hand side shows the behavior of a short circuit, because when we set the load impedance to 0, we're essentially creating just that, a short circuit. And on the right-hand side, we increased the load impedance to such a high value that we essentially created an open circuit. In the open circuit scenario, here on the right-hand side, the signals form a standing wave, indicating that no power is transferred from the generator to the load, since the load impedance is too high to allow any current to flow, and the power reflects entirely back to the source. This becomes more evident when we take a look at the trace and the envelope. The signal is standing and not traveling. You have these peaks and the envelope reaches to 0. And on the left-hand side, where we have a short circuit, we essentially have, since there is no resistance to consume the load, there is no load, you have a reflection of the signal. We can take a look at the trace and the envelope and see that the signal is contained and standing in between the generator and the supposed load. Everything that we send from the generator is reflected back through the transmission line and returns to the generator. So now let's stop the animation, and like we did before, the phasor diagram of the standing wave pattern, and we can see in both scenarios that there is a 90-degree shift between the voltage and the current. And this can be explained using the formula, where you can see here that there is a plus sign in the voltage equation and a negative sign in the current equation. So plus cosine theta and minus cosine theta results in a 90-degree shift in between the signals. The behavior can be seen here where we have lambda. The wavelengths are actually half lambda in between each repetition, which is what the equation is showing, that the 90-degree phase shift in between voltage and current is every half lambda. And that's all. Thank you for watching. If you have any questions, I'd be happy to answer them.